So here we have our first problem, and we're supposed to find the general solution for y prime equals 5 multiplied by y minus 17. After we find the general solution, we will find particular solutions with the given conditions here of y of 0 equals 25 and y of 0 equaling 1. So we will begin by treating this exactly the same way as we would treat any other differential equation. So we're going to begin by writing dy over dx and then setting it equal to 5 and then y minus 17. Now from here, it is a good idea to multiply both of these sides by dx, and then by doing so, we can cross out dx on this side and introduce it to the right. So then we're going to end up with dy equaling 5 y minus 17 dx. And then in order to fully separate the variables, we need to move the y minus 17 to where the y is on the left. So we're going to divide both sides by y minus 17, like so, and then on the right they will cancel out, and then we're going to end up with 1 over y minus 17 dy equaling 5 dx. From this point we can just take the integral of both sides of this equation, and then the integral of 1 over y minus 17 will be the natural log of y minus 17, and then on the right side we're going to have 5 and then x, and then do not forget your constant of integration c. If you're wondering why the antiderivative of 1 over y minus 17 is equal to natural log of y minus 17, we need to cover a few things. So the derivative dy dx of natural log u is going to equal to u prime over u. So let's say we're trying to take the derivative of, say, the natural log of 2x. In this case, u will be 2x. It is whatever is within the natural log. And then our u prime will be simply 2. It will be the derivative of u. So this will equal to 2 over and then 2x. And as you can see, the 2's will cancel and we're going to end up with 1 over x. So in this case, 1 over x will be our solution to the derivative of natural log of u. So just for the sake of practice, if we want to get the derivative of what we have right here, natural log, and then y minus 17, we know that our u will be equal to y minus 17. And our u prime will be, this y will turn into just a 1, and then the 17 is a constant, so it'll disappear. So then again, this is going to equal u prime over u. Our u prime is 1, and then our u is y minus 17. So if you take a look, this is exactly what we had on the integral over here. So now, in order to get this y out of this natural log, because we are going to solve for y, we need the general solution. We're going to introduce e, and then e will be to the power of both of these. So from here, you must recognize that natural log has a base of e, and because of that, we can actually cancel out the natural log with the e. So we're going to end up with y minus 17 on the left, and then this will equal to e to the power of 5x plus c. Now from here, you can move 17 to the right. So we're going to have y equals e to the power of 5x plus c, and then plus 17. Now I'm going to rewrite this as y equals e to the power of 5x, and since these two on the exponent are adding, we can actually multiply it by e to the power of c, and then we're going to have plus 17 still. And then after that, this e to the power of c is just a constant. So I'm just going to rewrite it as a, because a will still just be a normal constant such as this one. And then this will be multiplied by e to the power of 5x, and then plus 17. And then this will be your general solution. So now let's find our first particular solution. So the first one we have is y of 0 equaling 25, where x is 0 and our y is 25. So let's just plug in and substitute. So we're going to have 25 equals a, which is what we're trying to find, e to the power of 5 times x, which is 0, and then plus 17. Then we're going to have 25 equaling a, And then 5 times 0 is 0. Anything to the power of 0 is simply 1. And then plus 17. If we remove 17 from both sides, we're going to end up with a equaling 8. So now all we have to do is plug in a to our general. So we're going to have y equals 8e to the power of 5x plus 17. And this here will be your first particular solution. Now let me just remove some stuff so we can find the second particular equation here. So now we're going to have x as 0 and then y as 1. So we're going to have 1 equaling a, which is what we're trying to find, and then e to the power of 5 multiplied by x, which is 0 once again, and then plus 17. So at this point we can subtract 17 from both sides. So we're going to be left with negative 16 equaling a times e to the power of 0. Now, anything to the power of 0 is simply 1. So our a will be negative 16. And once we plug it into our general solution, we're going to have y equals negative 16 times e to the power of 5x plus 17. And this is your answer for the second particular solution. So in these next few problems, we're going to be talking about some practical applications to differential equations. So here we have a question that says, a continuous annuity with withdrawal rate N equals $17,000 per year and an interest rate R at 4% is funded by an initial deposit P sub O. And then part A is asking us, when will the annuity run out if the initial deposit was $37,500? And then later part B is asking which initial deposit, P sub 0, yields a constant balance. So in order to solve this problem, we're going to need the help of a specific equation. The equation goes P prime equals R multiplied by P minus N over R. So firstly, I want you to notice how closely this looks to what we had in the first place. So when we're talking about models involving y prime equaling k y minus b, if we put this equation side by side to this, we're going to have y prime equals k multiplied by y minus b. So look at the structure and notice how they're very close to one another. So this is just one variant of this model, the model y prime equaling k and y minus b. Now there are a few others that we will get to in this video, but this is the first one that we're going to talk about. So first I want to talk about some definitions. So what exactly does this equation mean? So we can start off by talking about P of t. P of t will equal the balance at time t. Next we can talk about R, which is simply the interest rate. And then N is going to equal the rate of withdrawal. It is also important to note this notation. So P of 0 will usually simply be P sub O, which is the initial condition that we're given. In this case, it will be initial balance. So next, notice how P of t will give us the balance at a time t. But also notice how we have P prime of t. So P prime of t is not the same as what we have over here as P of t. P prime of t can be seen as dp over dt, which is the change of balance over time. So it's kind of a rate of how fast it's doing it, as opposed to how much we have in the bank at that moment, which P of t would give us. So that is important to know, because part A is asking when will the annuity run out of funds if P sub O is $37,000. So this equation is not very helpful to us because all it's going to tell us is a rate of how fast the balance is changing. But what we want is when the annuity will run out. We want the balance to be 0. So what we have to do is get the antiderivative of this equation and bring it to P of t. So by doing so, we're going to be able to just plug in 0 to P of t and figure out when we will run out of funds. So using this equation, let's figure out what we do have. So we have n, which was 1700. We also have r, the rate, which is 4%. And when we write this as a decimal, it's going to be 0.04. And then we also have p sub o, which is 37,500. So let's begin by plugging in the variables that we do have over here on the right and plug them into this equation. So p prime we do not have yet. And then r we do have, it is 0.04. This is p, but it is not the same as this p sub o. P sub o will be what we're going to be setting the equation to when we solve this differential equation. This will be our starting condition to find when it's going to run out of money. We'll stick it on one of the ends and then solve for t, which will give us how long it'll take for the annuity to run out. So from here, we can simply write p again, and then n will be 1700, and then the r will be our rate one more time, which is 0.04. So now we're going to have p prime equaling 0.04 multiplied by p, and then minus, this will be equal to 42,000 and then 500. Now this is where separation of variables will come in. It might be a little easier to see if you write it as dp over dt, and then set it equal to 0.04 multiplied by p minus 42,500. So now you can see that we're going to want to separate this p and separate t's and put them on one side. Doesn't matter which side, but you're going to have to separate them. So we can begin by multiplying both sides by dt, as we have so many times already. So this will cancel with this dt. And then I'm going to move it over here. So we're going to have dp equaling 0.04 multiplied by p minus 42,500 multiplied by dt. You can then divide both sides by p minus 42,500. And then you'll see that these two will cancel. And then you're going to be left with 1 over p minus 42,500 dp equaling 0.04 dt. And now you can take the integral of both of these sides. On the left side, we're going to have the natural log and then the absolute value of p minus 42,500, and then this will be equal to 0.04 t, and then don't forget your constant of integration c. And I just noticed I added an extra 0 over here. We do not have this many zeros. I completely missed that. There we go. So I'm going to go ahead and just delete all these things over here since we do not need them at the moment, and make some space. So we can also begin by putting e to the power of both of these things, as we have been doing many times as well. So after we add the e's, we can cancel out the natural log there, and then we're going to end up with, on the left, p minus 42,500, and then it's going to be equal to e 0.04 and then plus c. We can then move the 42,000 to the right, and we're going to have p equaling e to the power of 0.04 plus c, and then plus 42,500. And once again, I randomly added another 0 for some reason, so let's go ahead and get rid of that. So then we're going to have p equaling e to the power of 0.04, and then we can just say that it's multiplying by e to the power of c, and then plus 42,500. And then again, e to the power of c, is this going to be a constant? So we can just write that as another c, and then it's going to be multiplying by e to the power of 0.04, and then plus 42,500. And then this will be your general solution for this problem. So let me go ahead and make more space on this side in order to solve for part A. So this will be part A. So now let's remember the notation that I brought up earlier. So I said that p of 0 can be equal to P sub 0, and then this is just simply the initial balance. In this case, they give us P sub 0, which was $37,500. So this can also be equal to P of 0, which is again our initial balance. So now using our general solution, P of t will equal to C times E to the power of 0.04 plus 42,500. And now notice the comparison between the original equation that I wrote down, which was the rate equation, versus this one. This one is not primed. So this equation here can give us our balance at any given time t. And talking about t, I actually forgot to add it in here. It's supposed to go right here, right next to the 0.04. I completely forgot about it for some reason. I don't know, maybe it just looked like a 1 or something to me. But I left it out here, but do not do that mistake. There is actually a t right here. So if we plug in t, just any t, we can get the amount of money that we have in the bank, the balance, as opposed to the original equation that was only able to give you a rate of how fast it was changing. So now that we have P sub 0 as 37,000, we know that that'll be equal to our balance at time 0. So we can substitute, instead of putting P of t, we can just put 37,500, and that'll be equal to C to the power of, not to the power, C times E to the power of 0.04 t, and then plus 42,500. So we can just write 37,500 equal to C to the power of E, not to the power but times E, and then to the power of 0.4 t. And t is 0 because at time 0 we have $37,000 as a balance, and then this will be plus 42,500. So let me go ahead and delete this to make more space. So if we subtract 42,500 from both sides, on the left we're going to have negative 5,000, and then this will equal C times E, and then 0.04 times 0 is 0. And then we also know that anything to the power of 0 is simply 1. So now let's plug our C into our general solution. So we're going to have P equaling negative 5,000 times E to the power of 0.04, don't forget the t like I did, and then plus 42,500. And then let me make some more space over here now. And then at this point we're finally able to really tackle A. So all we have to do is find out when the funds run out. Again, this equation is able to tell us how much balance we have, what our balance is at any given time. So we want to know when our balance will be 0. So we just have to set this equation down here to 0. So we're going to have 0 equals negative 5,000 e to the power of 0.04 t plus 42 and then 500. So if we move the 42 over, we're going to have negative 42,500 equal to negative 5,000 e to the power of 0.04 t. So now let's go ahead and divide both of these sides by negative 5,000. So firstly, our negatives will cancel, and then this will cancel this. So we're going to be left with 8.5 equaling e to the power of 0.04 t. And now, in order to get the t out of the exponent, because we have to solve for it, we're going to have to use a natural log. The reason we're going to be using a natural log is that there's a property in natural log that allows you to put the exponent to the front. So we're going to have natural log of 8.5, and it's going to equal the natural log of e to the power of 0.04 t. And then, like I said before, we can just move this to the front. So let me go ahead and make some space. So we're going to have the natural log of 8.5, and then it's going to equal 0.04 t times the natural log of e. And if you know, the natural log of e is just 1, so it's insignificant. So now to finish the problem off, we can just divide both sides by 0.04, and then these will cancel, and then we're going to be left with our t equaling the natural log of 8.5 and divided by 0.04. So if you plug this into a calculator, you're going to get t equaling 53.5016, and then it keeps going, but it doesn't really matter. You could round at whatever point you'd like. So what this means is that it's going to take about 53.5, if you want to round up, about 54 years for our funds to run out if our initial balance was $37,500. So there's your answer for part A. So let me go ahead and delete this and make some space. Part B is not as complicated as part A. So for part B, we are asked, which initial deposit P sub 0 yield a constant balance? So in order to figure this out, we're going to have to go back to our general solution, which was y equals c, not negative 5,000, that'll be the particular. We're going to have c and then e to the power of 0.04 t plus the 42,500. Really, this y was a p. It doesn't really matter, but just to stay consistent, yes, this was a p of t. So if we take a look at this equation, we have a few parts to it. We have the 42,000, we have the c to the exponent here, and then this is just a name that could be anything, so this part here doesn't really matter much. So if we take a look at these parts, which one of the parts is stopping us from having a consistent balance? So 42,500 will always stay 42,500. That'll never change. What is changing over time is this part, the middle, because it's e to the power of 0.04 t. So as time changes, this will change too. So if there were a way to get rid of this part of the equation, we can get a constant balance the whole time. So that is exactly what we're going to do. So we're going to have P of t equal, and then if our constant of integration, c, turns to be 0, and is multiplied by e to the power of 0.04 t plus 42,500. So we're going to have P of t, and since this is multiplying by a 0, it's going to be an automatic 0. So all we care about is the 42,500. So 42,500 will be the initial deposit P sub 0 that will give us a constant balance, and that is the answer to part B. So here's our next equation. We have a 51 kilogram skydiver jumps out of an airplane. What is her terminal velocity in miles per hour, assuming that k equals 10 kilograms per second for free fall, meaning no parachute? So before we even get started, I want to define what terminal velocity is. So terminal velocity is the max possible velocity by a free-falling object. So the reason that there is a maximum velocity and that you can't just keep getting faster and faster and faster is because of resistance. So there are different mediums by which resistance can affect you. If you're diving in water, then I suppose water can be the thing that's pushing against you. But in this case, we're free falling from an airplane, meaning that our resistance is going to be caused by air. So now that we've defined it, I'm going to go ahead and just remove it and actually get onto the problem. So in order to solve this problem successfully, we are going to need the help of a specific equation one more time. That equation will be v prime equals negative k over m multiplied by v plus m times g over k. So let's first define what some of these things mean. So first of all, v prime will be acceleration in meters per second squared. Negative k is going to be our air resistance. Constant, of course. It's a constant that they gave to us over here, 10 kilograms per second. And that is in kilograms per second, as I just said. M is going to equal the mass in kilograms. V is going to equal velocity at time t. And that'll be in meters per second. Finally, G will equal gravity, which is 9.8 meters per second squared. So I'm going to talk a little bit about the very top thing here, V prime acceleration, just a little bit, to maybe clear the air about what it means. So I'm going to go ahead and remove some of these things. So normally, you might come across equations such as this one. S of t equals maybe 9.8 times t squared plus 10t, and then plus a random constant. So this equation here is a position equation. So at any time t, you are able to get the position of anything. And if we take the derivative of this, so s prime of t, we can actually just write it as v of t. So the derivative of a position equation will give you the velocity equation for that equation. So s prime of t will equal v of t, which is the velocity. And then if we bring down the 2 here with the power rule, we're going to have 19.6 t plus 10, and then the 100 will disappear because it is just a constant. So now this equation here, whether you write it with s prime of t or v of t, this equation will give you your velocity at any given time t. And we can even go one further. So we can write it as s double prime of t, which will be the double derivative of our original, or we can write it as v prime of t, the first derivative of our velocity equation, and we can even write it as a of t. So the double derivative of a position equation will give you the acceleration equation, or the first derivative of a velocity equation will also give you the acceleration equation. So all we have to do now is take the derivative of the velocity equation, which is going to be 19.6, and then that t will disappear. This was a constant to begin with, so we're done. So your acceleration will be 19.6. So notice how v prime of t is actually what we have over here. So that means that we don't actually have a velocity equation in our hands, but an acceleration equation, which is what it says right up here. This is saying v prime equals acceleration, but in this equation we have v prime instead of just a of t. So if you were confused about why this is equal to acceleration, this is why. So which one of these three equations are we going to need to find the terminal velocity? So we know that at the moment we are here at the acceleration equation. So we want terminal velocity. So velocity equation will be the second one right here. So we need to go from here right up to this one. So that means that we need to take the integral to go one step before and get our velocity equation. Because of course, if we choose to stay in this equation, all we're going to get is acceleration, which is not very useful to us when we want terminal velocity. So let me go ahead and remove these things and make some space and finally get started with our problem here. So first, let's write down what we have. So we were given k, which is 10. It's in kilograms per second, but I'm going to leave out the units for now. We also know that g will just be 9.8 meters per second squared. That'll always stay the same. We were also given m, which is the mass of the skydiver, which is 51 kilograms. Now, what you want to do next is plug in what you know. So we still don't know what v prime is, and then we know k. So this is going to be negative 10 divided by m, which is the mass, which is 51. That'll be multiplied by v, and then plus, and then we're going to have m, the mass of 51, multiplied by 9.8, and this will all be divided by 10, the constant. Now, we're going to have v prime, and I'm going to leave this fraction alone. The decimal for it is really ugly, so I'm just going to leave it as negative 10 over 51. and then this will be multiplied by v plus, and if you plug all this into a calculator, you're going to get the decimal 49.98. And after doing these a couple times, you might know what comes next. So we can first write this as dv over dt, so the change of velocity over time, and then we can just set that equal to what we have already. And then, as we have done many times, we are going to divide both sides, not divide, multiply by dt. So what that does is once again cancel out the dt, and then I'm going to start on this right area over here. So that leaves us with dv equals negative 10 over 51 multiplied by v plus 49.98 and dt. So what we want to do next is divide both of these sides by v plus 49.98. So now you see that these will cancel on this side, and then we're going to be left with dv over v plus 49.98, and then that'll equal negative 10 over 51 dt. And now we can start taking the integral of both sides. So on the left, we're going to have the natural log and then the absolute value of v plus 49.98. And that'll equal negative 10 over 51 t, and then your constant of integration c. And now let me just remove some things so we can continue on with the problem. So at this point we can add the e's, and as we have done many times, we know that the e will cancel with the natural log. And then we're going to be left with v plus 49.98 equaling e to the power of negative 10 over 51 t plus c. Next, I'm going to just move the 49 over to the right, so v will equal e to the power of negative 10 over 51 t plus c, and then minus 49.98. So then we just go on with our usual business. So we're going to have e to the power of negative 10 over 51 t, and then we can multiply that by e to the power of c, since these are adding on the exponent, and then minus 49.98. So then we're going to have v equals, and then once again this is a constant, so I'm just going to write it as c. So we're going to have c times e, and then negative 10 over 51 t minus 49.98. And I'm actually going to rewrite this a little bit, so it makes this next part a little bit easier to see. So we're going to have v equals, and then I'm going to leave this c here for now, and this is going to be multiplied by 1 over e to the power of positive 10 over 51t. So notice how we lost the negative because we put it on the denominator, and then we're going to have minus 49.98. And now we can write that as v equals, you could have your c on top, and then e to the power of 10 over 51 t minus 49.98. And now let me just remove this in the bottom. So now you might be wondering why I manipulated my equation to look like this. So we're about to take the limit as x approaches infinity of our equation v of t. So you might be asking yourself, why are we taking the limit? So once again, we are looking for terminal velocity. And again, terminal velocity is just the max possible speed that you can achieve as you're free falling. So in a condition like this one, where you're falling for an infinite amount of time, just downward, then you will eventually reach the terminal velocity after a certain amount of time. And you will keep approaching that terminal velocity but never go past it. And that is exactly what a limit is. A limit will be approaching infinity on the x-axis. If you make a table, you're going to keep going infinity in terms of, in this case it's x, but it should be t. I'm going to change that in a little bit. but really this is t. So as time increases, we're going to keep falling faster and faster and faster, but at one point we're going to reach a maximum and we will not get faster than that because of air resistance. So what this limit will do is that it'll tell us what velocity it's going to be approaching after a really long time. So let me go ahead and get rid of this and also change this x variable. Since it is a t, we are doing this in terms of time. So if we start filling this out, this will turn into the limit as t approaches infinity, and then we're going to have c over e to the power of 10 over 51t minus 49.98. So now I want to introduce a law of limits. So it goes like this. So the limit as x approaches a of f of x plus or minus g of x will equal the limit as x approaches a of f of x plus or minus the limit as x approaches a of g of x. So notice how we're taking two different functions that are being added, and then we kind of just split them up into their own limits. So that's what we're going to do here. So let me go ahead and remove some of these things here. So let's rewrite what we have over here and split it into two different limit functions like it is down here. So firstly, we're going to have the limit as t approaches infinity of c over e to the power of 10 over 51 t. And then we're going to subtract the limit as not x, I was about to write x again, but as t approaches infinity of negative 49, well not negative, we already have the negative right there, of 49.98. So let me make just a little bit more space because I am about to introduce another rule. So the rule goes, the limit, let me write it in a different color so I don't confuse anyone. So the limit as x approaches infinity of a constant c over x to the power of r will equal 0 as long as it meets these conditions. The conditions are that r is a positive rational number and that c is any real number. So when we look at our equation over here, c will be any real number. We're not going to have any imaginary numbers or anything crazy like that. And our r, which in this case is our 10 over 51, is indeed positive. So we're good to go. So now, this thing here, this limit, will just turn into a 0. And then if you think about this next one, the limit as t approaches infinity of 49.98, well, since this is a constant, it'll be flat. If you graph this, the 49 will just be flat, and it'll just keep going like that forever. So as you move t in time into infinity, so 10 seconds, 20 seconds, a million seconds, it's still going to be 49.98 no matter what. Therefore, our limit as t approaches infinity of 49.98 will be exactly 49.98. So our final answer will be negative 49.98 meters per second. So this is our terminal velocity. As soon as we reach the velocity of 49.98 meters per second as we're moving downward, we will not go any faster. This is our limit. And if you're wondering why this is negative, it is because we're moving downward. So velocity will not always be positive, since it is a vector and it has both a magnitude and a direction. This is a little bit different from what speed is. Speed will actually equal the absolute value of velocity. So in this case, we have negative 49.98 meters per second. That is how fast we're moving, but we have a direction, not just a magnitude. So we're moving downward at a rate of 49.98 meters per second. Now, if we wanted just the speed of this, it's simply 49.98, because speed doesn't care what direction you're moving in. It only cares about the rate. That is it. It doesn't care about what way you're pointing. It only cares about how fast it's going. And then just in case you wanted your answer in miles per hour, then it'll equal to negative 110.80 miles per hour. And yeah, our problem did have miles per hour, not meters per second, so you need to make sure to make that conversion before you have your final answer. So here's the final answer for that one. So here is our final problem. So we have a cup of coffee cooling off in a room at room temperature of 20 degrees Celsius has a cooling constant of K equaling 0.096 per minute. A. How fast is the coffee cooling in degrees per minute when its temperature is T equals 76 degrees Celsius? B. The coffee is served at a temperature of 85 degrees Celsius. How long should you wait before drinking it if the optimal temperature is 62 degrees Celsius? So this problem relates to Newton's law of cooling. So the equation to solve this problem is as follows. So it's going to be dt over dt equals negative k, and then t minus t sub s. So now let's define what some of these things mean. So t is going to be the temperature of an object at time t. And then T sub S is going to be the temperature of the surroundings. And then finally K is going to be our cooling constant. So as you can see, we have a differential equation here. So what does this tell us? So this equation will output the change of temperature over time. So it's the rate of how fast or how slow something is cooling. So let's get started. So let me go ahead and just delete these things to make space. So part A is saying how fast is the coffee cooling in degrees per minute when its temperature is T equals 76 degrees Celsius. So a keyword here is how fast. Notice how it's not looking for any temperature or anything like that. It just wants to know how fast. So for part A, you actually don't need to do anything in terms of solving an equation, because as we know, this is going to spit out a rate. So now all we have to do is plug in everything that we know. So we know that K is equal to 0.096 as it was given to us here. We know that T, the temperature, is 76. That is when the temperature is 76 degrees Celsius. So this is 76. And then T sub S will be the temperature of the surroundings, which we were also given. It is right up there. It's 20 degrees Celsius. So now we're going to have dt over dt equaling negative 0.096 multiplied by t, which is 76, minus t sub s, which is 20. So then this will end up being negative 0.096 multiplied by 56. And then this will spit out negative 5.376 once you plug it into a calculator. So that is the rate at which it is cooling. And it makes sense that it is negative because it is cooling down, not heating up. So the coffee here is cooling at a rate of negative 5.376 degrees Celsius for every minute that goes by. So this will be degrees Celsius per minute. So now we have to be a little careful. Let's say that the question or the prompt was worded in such a way like this. Let's say if it was asking it is cooling at a rate of blank. So our answer is negative 5. But since we already acknowledged that it is cooling, there is no need to add the negative. It'll be the equivalent of saying I am backing up at a negative velocity. We already know we're backing up. We're backing up at a certain speed. But in this case, we already acknowledge that it is cooling, so there's no need to put the negative in there. So when it words it like this, you're just going to want to put 5.376, since this is just a rate and we know that it's cooling already. So now I'm just going to go ahead and remove some things to solve part B. So part B is asking, the coffee is served at a temperature of 85 degrees Celsius. How long should you wait before drinking it if the optimal temperature is 62 degrees? So notice how part B is not asking for a rate. This means that we're going to have to solve this equation here so we can get it back up to the temperature equation. So once we have the temperature equation and not just the rate at which the temperature is changing, we can plug in 62 degrees Celsius and find T and just solve for it to see how long we have to wait before drinking it. So once again, let's begin by writing down what we do know. So K is still K. It is still 0.096. And then T sub S will still be the same. It's still going to be 20 degrees Celsius because that's the room temperature. And then that is all we will be plugging in for now. So now we're going to have dt over dt equaling negative 0.096 multiplied by T minus the T sub S, which is the environment. So minus 20. And now I'm going to multiply both sides of this equation by dt. So we're going to cancel dt on both sides over here. And then we're going to have dt equaling negative 0.096 multiplied by t minus 20 dt. We can then divide both sides by t minus 20. And then we will see that we can cancel out this thing. So now we're going to have dt over t minus 20. And it's going to equal negative 0.096 times dt. So now we have fully separated the variables. So as we have done before, we will be taking the integral now that we have divided them up. So on the left, we're going to have the natural log of the absolute value of t minus 20 equaling negative 0.096 t. And then don't forget your constant of integration c. And then we're going to add our e's raised to the power of both sides. And once again, this e will cancel with the natural log. So we're going to have t minus 20 equaling e to the power of negative 0.096 plus c. So now let's move over this 20. So we're going to have t equals e to the power of negative 0.96 plus c, and then plus 20. And then there is a 0 right here. I just kind of missed it. So let me get rid of this side and continue. And then I did this once before. I had a t right here and then I just completely dropped it. Make sure you do not do that. It is very easy to lose the t, but if you lose it, then you will not get the right answer. So don't do what I'm doing. So now we're going to have t of t equaling e to the power of negative 0.096 t. And then instead of writing plus c, we're going to just multiply by e to the power of c, and then plus 20. So now this can be written as t of t equals c, since this is just a constant anyway, I'm just changing it to one letter, c times e to the power of negative 0.096 t, and then plus 20. So now here is our general solution for part B. Let me go ahead and get rid of these. So now we need to solve for c, and you might be wondering how in the world we're going to do that. Well, pay attention to the way this is worded right up here. It says the coffee is served at a temperature of 85 degrees Celsius. That means that at time 0, in other words the initial temperature, is or was 85 degrees. And then the 0 will be your time, so it happened at time 0 where the temperature was 85 degrees Celsius. So now let's plug it into our general solution equation here. So we're going to have 85 equaling c, and then e to the power of negative 0.096 times t, which is 0, plus 20. Now let's subtract 20 from both sides. So we're going to have 65 equaling c, times e, and then 0 times negative 0.096 is just 0. And now anything to the power of 0 is simply 1. So now our c will be 65. And now let's plug in our c to our general solution. So we're going to have t of t equaling 65 times e to the power of negative 0.096 t plus 20. So we want to know at what time t we will get 62 degrees. So all we really have to do now is plug in 62 to the end temperature, and then this is going to be equal to 65 times e to the power of negative 0.096, and then t is what we're solving for, and plus 20. And then once we subtract 20 from both sides, we're going to have 42 equaling 65 times e to the power of negative 0.096 t. Now, let's divide both sides by 65. So then the 65s will cancel on the right side, and then on the left we're going to have 42 over 65 equaling e to the power of negative 0.096 t. And now, what do you think we should do here? We need to solve for t, and at the moment it is an exponent, so there's no way of getting to it. So what do you think we should do? So it turns out that we will have to use natural logs. So the natural log of 42 over 65 will equal the natural log of e to the power of negative 0.096 t. The reason we're doing that is that natural log has a property that allows us to take the exponent of whatever is inside of the natural log and then just move it towards the front. So we're going to have natural log of 42 over 65 equaling negative 0.096 t times the natural log of e. So here the natural log of e is insignificant because it just equals to 1. So from here you can divide both sides by negative 0.096 and then do the same on this side, and you will see that we will cancel out the number, and then our t will equal the natural log of 42, that is a bad 4, 42 over 65 divided by negative 0.096. So once you plug that into a calculator, you will get t equaling 4.549, and that'll be in minutes. This means that at minute 4.5, our cup of coffee reached its optimal drinking temperature of 62 degrees. So in other words, it took the coffee about 4.5 minutes to cool down to 62 degrees. And that'll be it for this video. Thanks for watching, and I hope you learned something.